My name is Hai. I'm really happy to be here with you tonight. Let's just, have a big thank you to start with to our host tonight, Galvanize, who's been awesome. We have Alex and Matt in the back from Galvanize, and runs the Data Science Professional Development Meetup. So if you're interested in getting into data science or transitioning your career in data science, Aaron in the back right is the one to talk to because he runs a meetup devoted to that. But could we have a quick round of applause for our hosts, David and Alex from Galvanize? Okay, and now for the regularly scheduled program, we have Francesco, who was a theoretical physicist, and then, master's in theoretical physics, and then biophysics, got into software, and has now started his own company, Catalyst. And one of his programs is Data Weekends, where he basically just teaches data science for a whole weekend to folks, and it's getting more and more popular. So we're really lucky to have Francesco here today to teach us intro to data science.
Thank you, Hai. Hi guys, Francesco. I thought we'd spend maybe a couple of minutes to get to know each other. You have heard who I am, but I'd like to know who's in the room. So, how many of you have done data science before or are thinking of doing data science? Raise your hands. Okay. How many of you are coders or would qualify themselves as coders? Okay. Good. We'll spend about 3 hours together, slightly less. And so let's make them fun and let's enjoy ourselves. I'll go over a bit of theory of what data science is, although there isn't a precise definition. And then in the second half, after 8 o'clock, we'll do a quick Python exercise and code along. Okay, so here's some goals for what... can you hear me without the microphone? Or is it better with the microphone? Better with the microphone. Okay, I'll stick with it. Okay, we'll talk about what data science is, why it's so popular and why so many people are talking about it. We'll discover how it's used in products that we use every day, and we'll go through a bunch of examples. What are the skills that are required to be a data scientist? And learn what makes a good data science team. And finally, we'll talk about machine learning, which is a key component of data science, and play around with Python. Okay, I wanted to start with a trend. I assume you guys are familiar with Google Trends. If you're not, it's google.com/trends. You can type words and see how the popularity of a word has evolved over time. So I did a quick experiment and typed business intelligence and data science over a span of time that goes from 2005 here to today. And you can see that there is a very clear ascent of data science in the past few years. In fact, as we'll find out, the term didn't exist in the way we use it today before 2008, actually. So what is data science? Broadly speaking, it's the merger of stats with computer science. If you want to have a very, very loose definition of what data science is. Where does it come from? Well, the first people exploring data and finding it as a discipline that was not statistics nor maths, but nor engineering itself, but an interest for analyzing the data is John Takei in the 60s. But in fact, it was only in, as I said, 2008 that the head of data teams in two very famous companies here in the Bay Area, they gathered to exchange experiences and kind of share lessons learned on hiring people dealing with data, and they came up with this term, data scientist, as a person that was both using data and science to create something new. And since then, data science caught the news. Like, all articles are talking about it, and everybody wants to become a data scientist, and if you don't want to become a data scientist, after this talk you will want to. So, and in fact, this is an article, it's very recent, it's October 20th, 2015. It's a job that offers a great life balance. So consider it as a career, and there are great schools like Galvanize that can prepare you for that. So what made, why have we had this convergence of data and science to data science? Well, the fact is, companies are producing a gazillion of data. Okay, that's a slide from 2012. So I'll just read a couple of numbers. In 2012, Google was receiving 2 million queries every minute. And Twitter sent over 100,000 tweets every minute. And those are numbers that are like incredible already. But if you look at what happened in the past 3 years, they exploded. Queries went from 2 millions to 4 millions. Tweets went from 100,000 to 277,000, and so on and so forth. You can measure any company here in the Valley, it's producing a huge amount of data. To the point that 2 years ago, Science Daily was quoting 90% of the information ever produced by mankind was produced in the 2 years before then. So I assume 2 years after, it's even more than 90%. So why is that? Well, because we have a bunch of sources that are generating data. It's not just people, it's not just writers writing poems or mathematicians writing formulas, but it's a bunch of different data sources that are generating data. And these are the data generated by apps that we all use and websites. But these can be generated by objects that we wear or by apparatuses that are interfaced with the internet. Are you guys familiar with these things like the Nest or wearable devices or that thing, the phone? Yeah, I assume so. So yeah, and speaking of the phone, it could be iPhone or Android, doesn't really matter, but it produces data of many different kinds at a very high rate. Think of location data and behavioral data of how you use an app, or the purchase history in the App Store, or if you do in-app purchase, the purchase history in the app itself. If you download video and watch them, they have the data of what you're downloading and how often and what's their bandwidth and so on. Sensors, there are accelerometers on the phone that if you wear it, then there are algorithms that can tell you the steps or your physical activity and so on. Medical data, healthcare, and so on and so forth. So the phone is one of the many sensors that generate a lot of data. And there's a bunch of startups and companies that are using that data in pretty much any vertical. So whatever vertical you're working in, there is probably one or more companies that are doing big data analysis and big data products in that vertical. The hype is due to the fact that large and small companies use this data to achieve astonishing results. And for example, Google beats governments in predicting unemployment. Credit card companies, they use big data to prevent fraud at a large scale. So basically they are able in real time to understand whether a transaction is legitimate or is a fraudulent activity that someone is trying to steal money from them. Medical research, very, very interesting stuff coming up. And social media, I don't know if you guys noticed, but your wall in Facebook or any other social is personalized. You don't see all the data that your friends are posting, but you only see what Facebook thinks you will like and click. And everybody is doing this kind of personalization and segmentation of users to propose content. And data science relies a lot on machine learning. So relies on activities that are like of aggregation, filtering. So when you have data, you need to do these things to extract information. That's what a data scientist does throughout the day. Filtering, organizing the data, predicting an outcome, classifying, detecting anomalies. This is, for example, when you're dealing with credit cards, recognizing frequent patterns, recommend. So what I wanted to do is go through some applications, starting with things that we may be more familiar with. For example, keyword prediction. You type a word in a search engine, and it automatically suggests things that it assumes you're more likely to be searching for. That's an application of data science. Detecting fraud, we've talked about it. Routing calls in a call center. Depending on your call history and the kind of client, you may wait longer or shorter because there is an algorithm deciding how long you're likely to wait before you actually hang up. Predicting genes. How many of you have heard of 23andMe? Okay, for those who have never heard of 23andMe, it's a personalized genome company. Basically, you spit in a tube and they analyze your DNA and tell you the likelihood of risk of some illnesses. And you can extract very, very interesting information from genes. Vitals monitoring, also now very common in many wearables. Other things you may be even more familiar with. How many of you have noticed when you go on Amazon and buy something, it suggests, hey, you might also like this, and this other item. Yes? Oh, okay. Oh, by the way, if you have questions, don't wait for the end. Raise your hand and interrupt me. I don't want to do a monologue. It's more fun if it's interactive. Netflix, same thing. Recommending movies. Netflix, by the way, became very famous because it's one of the first companies that actually ran a prize for data science. So in 2004, they put $1 million for the team of people, of statisticians or computer scientists that could improve their recommendation system by 10%. And the prize was actually won, and this kind of spearheaded the future of like data science competitions, which then became big thing. Application of deep learning, this is pretty recent. From an image, generate a caption that is human readable. And this is also very recent. Have you noticed that now many websites don't ask you to input a CAPTCHA, just ask you to click, I'm not a robot? So in the back end, what happens, they are analyzing the movement of your mouse and deciding whether that looks like a human moving the mouse or a robot hitting the click. And the jury's out for how long it will take to the hackers to actually fake the movement of the mouse, but so far it seems to be working pretty well. Other applications, social network analysis. We've talked about it a little bit. So grouping. This is actually a free app from LinkedIn. You can go and research LinkedIn and analyze the network of your friends and see how they cluster around your past, for example. I know in my case I have 3 groups, one my Italian friends, one my American friends, and there is almost no connection except for 2 that are moving back and forth from Silicon Valley and Italy. Sentiment analysis. Do you guys know what sentiment analysis is? One person? What about? Okay, sentiment analysis means automated detection of the sentiment in a tweet or in a post. Sentiment being, is it a positive comment or a negative comment? Marketing applications for this is huge, because if you're a brand page, say on Facebook, you would like to know whether the people commenting on it are mainly positive or negative, reacting to, say, a piece of news. So, or you think if you're a celebrity and you have your page with 10 million fans, there's no way you can have people monitoring all the conversations, and you would like to know if you say, hey, my new record is out, you'd like to quickly gauge whether it's appreciated or not. So that's sentiment analysis. Spam filtering. Have you noticed we don't have spam anymore? That's machine learning. Document classification. Basically going from a bunch of documents that are untriaged to knowing which document is what. So document is a receipt or a claim or an application or whatever. And you can also have applications in prediction, for example, of trends. So predicting the price of a house. That's what Trulia and Zillow do all the time. They even have a registered mark, it's called Zestimate, which is their own patented algorithm for estimating the price of the house. Stock market prediction. I'm not sure exactly of the fraction, but more than 50% for sure of the trades nowadays are automated, so they're robots trading stocks. It's not humans any longer. And those trade based on algorithms. So I mentioned the wall. So here there is many applications of data science. That's a post that somehow was considered interesting to me. I'm not sure why. It's a friend from Italy. Here is suggesting people I may know. Not so good, I don't know that guy, but whatever. And groups that I could be interested in because some of my friends are also in those groups. So sometimes data science is doing pretty simple things, like, hey, you have 4 friends there, so you might be interested in that. Sometimes it's doing much more elaborated things, like the CAPTCHA example that we did before. So all this is possible because there are these guys called data scientists. And so what is a data scientist? Well, somebody suggested this Venn diagram where a data scientist sits at the middle of 3 domains. Hacking skills, maths and stats, and expertise of the domain. It also went one step further and labeled what are the incomplete intersections of the 3. So if you have hacking skills and you know stats, but you don't know anything of the domain, you're probably just a machine learning expert. But it may be hard for you to give a valuable business insider. And remember, at the end of the day, a data scientist works for a company and needs to provide business insights. It's not a researcher that just needs to produce a model. That's what a researcher would do without hacking skills, and the danger zone of hacking skills and expertise, I won't comment on that. What are the skills? Well, you must know stats and machine learning. Those are prerequisites. You will use machine learning pretty much every day. Machine learning relies a lot on statistics. So beyond the simple vanilla application of ML, like we'll do today, you need to be familiar with both domains quite heavy. And you need to be a programmer. More and more, a data scientist is often required to be also a data engineer. So not only to be able to build a model, but also to be able to translate it into production code. Or at least to interact with the engineers that will build the production code in a meaningful way. So you cannot just handle the script and say, you guys copy it and figure it out. Databases, of course. And then there are some soft skills that are as important, if not more. Definitely being a curious observer. Noticing patterns that may be even obvious is a good starting point. Sometimes you will find through the algorithms that the result is completely unexpected, and that's when it's a lot of fun. But a lot of time, starting from an intuition is a good starting point. And then you rigorously follow a process and iteratively get to a conclusion that may be different from your intuition, but at least you had a starting point. That's where the taking risks come in. You don't know the answer at the beginning, otherwise you wouldn't need machine learning to get it. And so sometimes you have to take a risk and say, hey, I'm going to explore that direction and see what the result is. Since you're working in industry and not in academia, you need to have a product sense to talk with product managers. Oftentimes, if the company is a data company, there are data products. Could be data products for the outside, or you could be doing data products for the company, for other stakeholders in the company to use. And so you need to have that intuition. And finally, that's probably the most important of all, you need to be able to tell a story. Because you will be the one that translates the insights you found from the model to a story that you can then tell to the CEO or the product manager or the VP of engineering to convince them that a certain direction makes sense. And selling numbers is really hard. So being able to translate those dry numbers into a story that makes sense to a non-technical counterparty is very, very important. So important that all those skills are often not all found at the top in one single person, but often you have a team of people that share a common goal, and some are better prepared than others in a specific domain. So depending on the phase you're in, if you're in the discovery phase, the skills that you require are more like domain expertise and exploratory analysis and modeling. So the people involved in the first phase will be people like the domain expert and the data scientist. In the modeling, it's definitely the data scientist who's the most involved. Then when you start to see, okay, the model makes sense and I need to integrate it into production, it's going to be the domain expert again, but then the developers. And then it becomes more and more the developers in the later stage of like maintaining the product. So storytelling happens here. Because before the company decides, okay, we allocate resources to actually productize this, they need to be aligned and convinced that your model makes sense. And that's why a data scientist needs to be a good storyteller. Yes?
You saw that you have worked before. And
This?
before.
Yep.
And some like you get one that's the expertise in the world, and you have the hacking skill and the best skill top. Right?
Sorry, I didn't understand the question.
You have the hacking skills and methods of technology at the top.
Hacking skills?
Yeah, the big balls, the clutch. Yeah.
Yes.
I sort of do that when you do the things that count, like a little more than the knowledge of the skills. Am I wrong about it?
What do you mean?
I think that hacking skills and technology will be more important
The domain. Okay, it's definitely, for a data science project, it's definitely very important that there is a domain expert in the team. So you could think of this as either a data scientist or a data science team. In order to do data science, you need the three. Now, is one person that is a jack of all trades and knows everything, or are these three things spread across 1, 2, 3, 4 people? Depending on the problem, sometimes it's even necessary because the domain is so vast that you won't be able to have all the knowledge in one person. But in order to do a data science project, you need the three. Does that answer your question? Okay. Any other question? Okay, let's do a raise of hands. How many of you after this are more curious to be a data scientist? How many of you are more scared to be a data scientist? Okay, so the curious wins the scared, so that's a good thing. Okay, I mentioned that machine learning is a core skill, and so we'll spend the next few minutes talking about machine learning. And what I'll try to convince you is that you are already able to actually do machine learning, although you don't know that. And I'll show you why. What do you see here?
Correlation.
Raise your hand and talk. Huh? Yeah.
Correlation.
Huh?
Correlation.
Correlation. Okay, he said correlation. Can somebody else explain what he means? Yes.
Positive correlation where weight is directly related to height.
Yes, okay, so let's start talking about what this plot is. This is a plot of humans, okay? So I assume each dot represents a person, okay? And I have weight and height. So each individual is represented by a dot on this plane of weight and height. And what's your name? Farsha said there is positive correlation between weight and height. Does everybody see that? Who doesn't see the positive correlation? Okay, yes, exactly. So you all know already how to do data science. That's exactly what I said. There is a positive correlation. It's the visual cortex. It's actually a very, very good pattern recognizer. And it's immediately visible to us that this cloud of dots is not random. There is some sort of underlying pattern. Okay? What about here? What is it about and what do you guys see? Huh? Two groups, yes. Okay, let's start from the beginning. This graph is plotting ISPs, Internet Service Providers. So each dot is a different ISP. In the x-axis we have the download speed, and in the y-axis we have the upload speed. What else do we see? There are two groups, one is red and one is blue. What else? Yes?
If the upload speed is more, the download speed will be fast.
Okay, so you're suggesting there is again a positive correlation of sort?
Yeah, with the speeds.
Between the upload speed and the download speed. So in general, if you're higher in one, you will tend to be higher in the other one? Yes, that's correct. Does anybody see anything else? Yes? What's your name?
My name's Aaron.
Aaron?
Yeah, the two groups are clustered together.
The two groups are clustered together. What do you mean?
Red dots are close to the red dots.
The red dots are close to the red dots, and the blue dots are close to the red dots. To the blue dots, yes. Anyone else sees anything else? Yeah?
There are 2 points which are extreme as compared to the other point. can be outliers as well.
Which ones are those?
The two red points in the fast.
These?
Yeah.
You're saying these guys are kind of on their own, far away from everyone else.
Yeah.
Yes, although, I mean, this guy is pretty short, close, and these guys are pretty close to these guys, so I'm not sure to call it that far, but I see what you mean. Okay, so let's recap what we said. We said there is probably a positive correlation, and the red dots are closer to one another, and the blue dots are closer to one another. So it's almost like there was a separating imaginary boundary between the two classes, the slow guys, the blue, and the red guys, the fast. So if I had a dot here, would I call it a red or a blue? Would I call it a fast or a slow? Huh? Red. Based on my imaginary boundary, if I had an ISP here, I would call it a fast ISP. That's called the classification task. What about this? Yes?
There are two distinct groups.
There are two distinct groups. Okay. Which ones are they?
There is the blue group at the top and the black at the lower left.
This or this? All of this. And then, I guess, that. Yeah. So this is showing a bunch of flowers. Each dot represents a flower here. And I'm measuring two attributes of the flowers, the length of the petals in centimeters this time, and the length of the sepal. And yes, there seem to be two groups. Actually, if you go and check the data sets, there are actually three groups, but these two don't separate well. But yeah, visible here there are two groups, and if I didn't know anything else, I could probably group them into two separate classes. So you've just solved, collectively, three examples of machine learning tasks. First one was a regression. Find the correlation, find the model that predicts a function that connects the x and the y's. The second was a classification where you have separate classes and you're asked to predict the class of a new point. And the third is a clustering, where you don't know the classes and you're asked, are there subgroups where I can group my data? So machine learning, as a branch of science and computer science, dates back again to the 60s, late 50s. And thanks to a pioneer in artificial intelligence here at Stanford, Arthur Samuel, he said, machine learning is a field of study that gives computer the ability to learn without being explicitly programmed. And that's the key. You could define a rule arbitrarily and say, this is the line that separates my data. But what machine learning does is automatically find where that line falls. So how does it do it? It doesn't memorize and recall the data. In some way, it learns to generalize from examples you give it. So you start showing the machine examples that you know, and if the algorithm works, it will learn to predict on new examples. So how do we do that? First method is supervised learning. That's what you do when you solve these kind of questions. Is it spam or not spam? You take a bunch of emails, you manually label them, or you use a service of people that manually label them as spam or not spam. And then give examples of those emails to the algorithm saying, this is an email that I know it's spam. And you send another one and say, this is an email that I know it's not spam, and so on and so forth. And the more examples you provide, the better the algorithm becomes. Have you ever noticed sometimes Google Gmail says, would you like to send this particular message to the spam team for them to analyze? Anyone notice that? Yeah. So that's exactly it. You're labeling an example where they noticed that their algorithm is not doing well, maybe went in the spam folder and noticed that there were emails that you didn't want to be labeled as spam. And so you take it out and Google says, hey, help us learn, help us improve the algorithm. Another example is stock prediction, where I know the history of stocks. So in that case, my labels are the past prices. The other case is unsupervised learning, which is where I don't know what the labels are. So in that case, what I'm looking for is an answer to the question, is there a deeper structure in my data? Can I look at my data from a higher, more abstract perspective and understand it as not just a bunch of points, but actually as 4 groups of very different points? Let's stop here for a second. All the applications we've seen before, which ones were supervised and which ones were unsupervised? If you don't recall them, let's just name a few applications that you can think of, and let's see if they are supervised or unsupervised learning.
The one on Facebook where it asks you, do you want to, maybe this is your friend or something?
Mm-hmm. Would that be supervised or unsupervised?
That would be supervised, yeah. But yes.
So you are giving the supervision when you hit yes or no, correct? And in the beginning, it's also supervised because they know your friends, so they have an initial group of labels. Yes? Different example. Thank you.
House price prediction is maybe unsupervised.
Why is that?
Because it is studying the market trend and then giving us the information without any input from our side.
Yes, but at the same time, when you do a prediction, you are starting from some factors. Could be, I don't know, to make it simple, the size of the house or how old the house is, and so on. And you have some examples of known prices. So you can base your prediction on past predictions that are actually labeled. So I would actually say that's supervised. Yeah? Okay, another example? Yeah. Yeah.
The tracking Google searches, that's supervised?
How so?
Because it's tracking all the entries people make as they come, so it's counting them. And it recognizes the...
You have past searches, and so yes, I agree. What about if I start from a database of user demographics of my app, and I just want to understand what kind of users are using my app? Would that be supervised or unsupervised? Let's say I collect the age and the in-app behavior and a couple of other questions that I asked the user. Yeah.
I think it's unsupervised because you don't have a label.
Yeah, in that case, I don't have a label, so it's unsupervised. And what could be like interesting things that I could discover?
You could see specific
groups using your maybe specific demographics of users who are using your app more compared to the other users, so you could group them and say, okay, this is my top customers, these are my ideal customers, and these are my customers that I'm not currently using, so you could think about features on how you can also bring them into your product.
Correct. Yes, absolutely. And there are many companies actually doing that. One example I know for sure is Uber. They take the data from their drivers and they segment it by looking at the patterns of use of driving. So through the 24 hours of the day, how do drivers drive? And what they found was that there are actually different populations of drivers. So you can imagine what could they be if you have experienced going with Uber drivers. For example, there are some drivers that just drive 9 to 5 and they do like weekdays 9 to 5 and that's their standard job. What could be another population that has very different behavior?
College students.
College students, how would they drive?
They might not have specific times. They might, that schedule would be very flexible.
Yeah, so they probably would be like random at some points of the day in the week. What could be another population that could be different from these two?
An infectious disease.
Huh?
An infectious disease.
An infectious disease. How so?
Sometimes we find infectious diseases arising in certain parts of the world, the globe, that are not predictable, particularly viruses. And it's oftentimes not particularly obvious from an epidemiological perspective.
Okay, so in the context of supervised and unsupervised learning, what would you be would this problem even apply, or it's a different problem that probably requires different tools?
I think it's from an unsupervised perspective, particularly in the rate of genetic abnormality and change over time. That's what I'd be looking at.
Okay. So I'm not an expert in diseases, so I wouldn't be able to comment on that, but possibly. Okay, one last example, yes?
Not an example, but a quick question.
Yeah.
So, is it okay to say that we start, like every instance of an observation starts with unsupervised learning, and the more you get the data, it goes towards supervised learning?
Yes, that's a good way of looking at it. If you are completely new to the domain and you already have data, you probably start from an unsupervised problem. On the other hand, if the data you're collecting comes from an experiment you've designed, you might be collecting the labels at the same time. So it really depends on how you acquire the data, right? Because you could be acquiring the data with the labels, say for example clicks. I open my new website, I have 0 data, and what I'm trying to do is predict the user behavior to click on a specific link, okay? So my inputs will be where I placed the objects on the page and how the user metrics are doing, like how long is he spending on different parts of the page. And my label is going to be the click or not click. So in that case, when the first user comes, I have the first data point and I also have the first label at the same time, right? A completely different example is, for example, what we were doing in my previous company, which is a wearable devices company. We had people wearing our wearable and we collected all the raw data from the sensors. In that case, we had a very, very large data set of unlabeled physical activities. So we could see like wiggles in the accelerometers, but the person hadn't told us, I'm jogging. And so in that case, the big problem is how do you actually label them in an unsupervised way? Yes. Okay, so the steps for going from the data to a model can be summarized as follows. I start from data. And it could be of many forms. It could be text, documents, could be images, videos, could be transactions, so database records. It could be user behavior in a very unstructured way. It could be revenues, could be anything. And that's the collection phase. Then phase 2 is I process that data. I'm going to clean it, transform it, find out if there is missing data of sort, define what the features are, so what are the things that I will use as predictors. Then I build a model. So the model will use the features extracted from this data to give a prediction. And this prediction in the simplest case is going to be a yes-no prediction. Could have a more complicated prediction, but the simplest case is a binary yes-no prediction. And then at some point I need to be able to say, was that prediction a good one? So I need to have a way to assess whether my model was performing well or not. And I need to do this before I deploy the model, because I want to be able to compare, for example, different possibilities of a model and see which one is performing better on my data, the data that I already have. And then when I find the best model, I go to the engineers, I talk to them, or I go to the stakeholders that are asking me for the model. I say, this is the best model we can do so far with the data we have. Let's deploy it, and let's gather more data so that we can build a better model. So the life of a data scientist is spent in this kind of iterative loop where you continuously go from collecting data, cleaning it, building a model, and then checking how good you're doing, and then iterating it, and so on and so forth. And I want to spend 1 minute to stress and emphasize one particular thing, because it's very important. This is also very similar to the scientific process, in a way. I collect data, I find a model, or discover a model, and then I formulate a prediction and do a new experiment. The difference here is that the time constraint between being a scientist and being a data scientist are very different. A data scientist is in a production environment or in a company, and so this part is time constrained. You need to get to here quite quickly so you can iterate and get better. Instead, very often, if you're in research, you're optimizing for perfection. So you don't care if it takes you 6 months longer if you can get a better result. So there are very, very different approaches. In one case, you're optimizing for speed and time of execution. In the other case, you're optimizing for absolute accuracy. And you need to be able to understand the difference and skew towards execution if you're in an industry environment. That's very important. Okay, what does an actual pipeline look like? You will have the data flowing in, you separate your data into a test group and a training group. You have your algorithm that builds the model. You check how good the model is on your testing data. Have some metrics that will tell you how good it is, and then discuss with the other people about how to improve it. At the same time, you generate the prediction on new data, and you ask the user for feedback in order to improve the model, and so on and so forth. That's just another way of displaying the same process. Okay, so as we said, in the machine learning process, you go from data to something that we call features. So for the sake of the argument, I'll take a simple data set, which is a table. That's the simplest data set you can get. And I just want to give you some names so that we all speak the same language, and when you talk to a machine learning expert, you know what he's talking about. So the first thing is a row. In this table, let's see what it displays before. So it's a bunch of clients of a bank, presumably. For each of them, I have the age, I have the gender, the annual salary, the months in the same residence, how many months he's been in the job, whether or not he has debt and how much, and whether or not he paid off the credit that he had. So one row in my table is called a record or a data point. Okay? And the columns, age, gender, annual salary, and so on and so forth, are called features. Now, if I was doing an unsupervised learning problem, that's all I got. I don't have the labels. I only have the data and the features for the data. So in this case, I would be looking at things like, do my users cluster? Are there people behaving in a similar way, that they have the kind of similar debt, similar age? And that's quite likely going to be the case. People in similar age groups tend to have similar debt behavior on a large scale. On the other hand, if I was doing a supervised learning exercise, I would have the labels. So I would know what people are doing, whether or not they are returning their debt. And in that case, the goal would be to generalize this to new data. So when a new client signs up, I want to be able to predict whether or not he's going to return his debt or not. And that's supervised learning, which is this: finding boundaries or predicting quantities. So the simplest classification is a binary classification like this one, where you have just two possible outcomes: yes, no, blue, red, and so on and so forth. How do you solve this? There are many, many methods, and altogether they go under the name of classification methods. Historically, first ones to be invented, although it seems odd, were neural networks. Only computers were so slow back then that we couldn't make use of them very much. And that's why we use them today, because now we have GPUs and we can run very, very large calculations on what essentially is a graphics card. Decision trees came after, and we'll talk extensively about decision trees today. And then support vector machines, and logistic regression, and naive Bayes, and so on. Okay, so decision trees are very, very commonly used for two reasons. First, because they are fast once you've trained it, but also, and more importantly, because they're very easy to understand. So let's say I want to build a model here based on this data. I have my 3 data points, and I want to build a simple model that, looking at these fields, will predict whether the outcome variable is a yes or a no. Okay? What a decision tree does, here, it builds a set of choices that split my data. So in this case, for example, I take the age of the person. Is it greater than 30 years old? If yes, then I say it's not a risky record. If no, I ask a second question. Is the salary above a certain threshold? If yes, well, not risky. If no, then risky. And I can imagine building much, much larger trees, like where each node is a question separating some data on one side and some data on the other side. And I built all this hierarchy of questions, and each final node, the ones in green, are my labels. So when I end here, this is an answer. So the nice thing about decision trees is that once I've trained it with my data, I can forget about the data. The only thing I need to know are the rules. So I don't need to keep any of the past data in memory. I need the data just to train the decision tree. But then once the tree is formed, all I need is to know that this question is asking, for example, is the age above 30? Yes, no. Is the salary above 20,000? Yes, no, and so on and so forth. So that makes for a very fast and compact model, because the only thing I'm keeping in memory is the rules. Also, it makes for a very easy to communicate model, because it's, I guess, if you go to, say, a marketing person and say, hey, I've found this great model that predicts customer churn, and it's based on a sequence of questions that essentially look at things like how long have you been using the phone, how long have you been a subscriber to these specific offers, and how often do you use the phone, and so on and so forth. It's very easy for a person that is non-technical to understand this kind of reasoning. And also, it could generate some ideas on how to tackle the problem. So, for example, if you're trying to predict churn, and you're trying to devise a marketing strategy to counter that, you could be inspired by saying, oh, look, our model says that we lose this population that has these specific characteristics, certain salary, certain usage pattern, and so on. So, it's very, very commonly used, so much so that there is more than one platform as a service software that basically you can sign up and get that as a service in the net. A different model that solves the same problem is called k-nearest neighbors. So what does it do? It looks at surrounding points and decides by majority vote. So in this case, I have 3 classes, not 2. I have the green, the blue, and the red. And my new point without the label comes in, and I ask, is it a blue, a green, or a red? What is it going to be? Why blue? Because in this case, I'm taking the 3 points that are nearest to the gray point, and I'm saying what's the majority of them like, and I'll choose the majority because I'm a conformist. So if I have a new data point here, what color will it be? Green, of course, because everybody else around this is green. And if it's here?
Blue and orange tie.
Blue and orange tie. Well, let's see. This is definitely very close. Then this, so we have one red and one blue. And these are probably very, very tight. So yes, this is going to be hard. So what I can do though is take a different number of neighbors and say take 4, 5, 20 of the nearest points. So if instead of taking 3, I took 5 and I'm here, it would probably be blue because this guy would win, right? So 1, 2, 3. Although this guy is also close. Let's see. Okay. Any questions on the KNN or the decision trees? Yes.
Just very briefly, the validation portion of this. Can you explain that?
How you validate?
Yeah.
Yeah, I'll go after the models, I'll go to that. Yes, absolutely. It's a very important thing. Yeah, I will not leave it out. Okay, neural nets. Super famous nowadays. The way they work, it's a bit technical. They take the features in input and they essentially do a weighted sum. And then, based on the result of the weighted sum of the inputs, they take a decision whether or not to fire the neuron, i.e. to pass the input to the next layer. And they're built in such a way that there are many layers, so that information flows through the network until you get to one output layer that gives the final decision whether it's a yes or a no. Very, very powerful. They have a lot of free parameters because basically each of these arrows has a free parameter. So you need a very large amount of data to train a neural net. But you can do amazing things. Recognize faces. Have you noticed that now they don't even ask you to tag people on Facebook because they already know the names? That's because we've been submitting so many labels that now they know all the faces. Recognizing the content of an image. Look at this, like container ship, lifeboat, amphibian, fireboat, drilling, but container ship is definitely the most likely. This, Dalmatian, grape, elderberry, etc. Very powerful. Google Translate uses that, for example, amongst other things. Okay, SVN support vector machines. What they try to do, the algorithm tries to maximize the boundary of separation or margin between the two classes. So it looks for a way to separate my points such that the margin between the two classes is the largest possible. Now, if the two classes overlap, the separation will not be so net, so that's why it's called soft margin. You can introduce a softness parameter. But let's not go into that. The important thing is that it can work for highly dimensional data. Used, for example, in spam filtering a lot. Last one, it's called logistic regression. And although it was discovered later, it's actually quite simple. And the nice thing is that it can be parallelized. So you can use it on very, very large scale data. And it's used in many applications, for example, search ranking, online advertising, click prediction, and so on. The nice thing about the last two, the logistic regression and the support vector machine, is that not only they give us a class, but they also give a probability of belonging to a certain class. So potentially, if you get a data point that in this specific example is neither blue nor red, but it's a green that you've never seen before, this model will tell you it's a low probability in both classes. It's a low probability that it's a red, and it's a low probability that it's a blue. Supposing that it looks different from both. Okay, so we've talked about this, the models. We had a question which is, how do we actually do this? So that's the next step. And the simplest way of doing it, it's called a train test split. So somehow, of the data I already have, I will use part to train my model and part to test the output. And it's actually simpler than you would think. As simple as I take my data, all the data I have available, I split it, I hold out a part, okay? I use the remaining part. Generally, I do a split of like 80 to 20 or 70 to 30. I could do 50-50, but I take the larger part to train my algorithms. So I have a trained model, okay? And then I take the testing data and I evaluate the performance on the model on data it has never seen. Make sense? Yeah, so simple as I train the data I train the model on some data, and then the data I have not used but for which I already have the labels, remember, I use that to check whether I'm doing well or not. And in the simple case of the binary classification, where you have only two possible outcomes, which is positive or negative, okay, or yes, no. I can dig a bit deeper and see how well am I doing in this two-dimensional matrix, which is called confusion matrix. So let's say I'm testing for whether or not the user clicks, and the model is trying to predict the click. So condition positive means the user has clicked. Condition negative means the user has not clicked. Test positive means I predicted that the user would click. Test negative means I predicted the user would not click. So if I predict that if the user will click, and in fact he has clicked or she has clicked, that's called a true positive. Vice versa, if I predict that it's a negative and it has not clicked, that's called a true negative, because my prediction was correct. Okay, and then there are the two cases where I do a wrong prediction. I could be predicting wrong on the negative side, or I could be predicting wrong on the positive side. And those have respective names of false positives and false negatives. Okay? So, can anyone think of a case where these two matter in a very different way? Where it's actually not the same thing to err on the side of a positive prediction and on the side of a negative prediction? Yes?
Sorry to bring up medicine again. We see this all the time. False positives and false negatives.
Okay, so make an example.
Yeah, somebody can come in with, again, a disease of any kind. And, you may test and it comes out negative.
Yeah.
But you're sure, so you test again.
Yeah.
You should try to keep testing until you get it.
Yeah, so in that case, what's worse? To tell somebody that he has an illness and he actually doesn't? Or tell somebody that he's sane and he's ill?
Well, they're just as bad.
Huh?
They're just as bad.
They're just as bad?
Yeah.
I wouldn't say so.
Go ahead.
Because if you tell somebody that, and it's actually what you just told me, because if you tell somebody that he's not ill, like the test comes out negative, but he's ill, if you don't test again, that person might die. Let's say you're screening for cancer, and the screening comes out negative. That's actually a far worse error than telling somebody, hey, you're ill, and then you find out that he's not. In one case, the person might die. In the other case, well, he gets scared, maybe he sues you. But depending what you're optimizing, if you're optimizing for survival or for avoiding lawsuits, you're...
So you are by nature very conservative.
Exactly.
Yeah, so you can't be that way in medicine.
Huh?
You can't be that way in medicine because the false positives, will lead you to treating a patient incorrectly.
Okay.
Yeah, so you have to check yourself.
You have to be conservative on the other side too.
On the other side.
Okay. Fair enough. Understand. What could be a business case of similar, like, not equal results if you predict error in one side or error in the other side?
Advertising.
Okay.
Like somebody judging advertising based on their shopping pattern.
Okay, and what would be the error in that case, and why would it be bad in one case, and why would it be good in the other case?
Waste of money if it's you send advertising if it's incorrect prediction.
Okay. Whereas if you don't send it, it's just a missed opportunity. Yes. What about fraud detection? If I label a fraudulent transaction as a legitimate transaction, is it better or worse than if I prevent a legitimate transaction because I think it's fraudulent? Same thing? It's safer to err on the side of blocking a bit too much than to err on the side of letting money be wasted. So yeah, in that case also, it's not the same thing to err on the side of positive or on the side of negative. Okay, so from these, I can define total score, which is called accuracy, and I could define other scores depending on what I want to optimize, but to keep things simple, I just put the accuracy here, which is the number of true positives plus the number of true negatives, so this plus this, divided by the total. So essentially it tells me what's the fraction of predictions I got correct. Okay? And let's make an example. Let's say I'm screening for cancer, and my data set is composed by 20% of images that have cancer and 20% of images that don't have cancer. Okay? So I have a bunch of images, say brain scans, and I have 20% of them which have cancer and 20% of them which don't have cancer. Let's say I make a very, very, very dumb model that says nobody has cancer. What's the accuracy of that model?
80%, 60%, 80%.
Let's see it together. So, how many true positives do I have? Well, I'm saying that positive here has cancer. My test positive is 0 because I'm predicting everybody doesn't have cancer, right? So true positive must be 0 because I'm not predicting anybody with cancer, right? So this is 0. What about true negatives? Well, I'm saying 100% of them have cancer, but only 80% of them actually have it, so I'm correct 80% of the time, right? So 80 plus 0 divided by 100 is 80%. So depending on what the class balance is, my benchmark with a very stupid model could be as high as 99% if the skewness of the class is high. So I always have to keep that in mind. How many examples of each class I have? Is it a balanced data set or not? Okay? And that's going to be my benchmark. Okay, I think it's a good time to take a break, maybe take a 5 minutes break, and then we get our hands dirty with Python. If you have questions, I'm very happy to chat, both on what you've just seen and on being a data scientist in a company or whatever. I was asking me about Hadoop. If you have to start today, start learning Spark instead. It's basically where the industry is going in terms of big data. Julia, very promising, interesting, fast scripting language, and many, many others. But Python has a pretty comprehensive ecosystem of tools. Starting from the foundation of Python and Pandas, which is the library that allows us to deal with data. We'll learn about it today. And then you have a very nice interactive computing environment, which we'll use today. It's called Jupyter Notebook. And then you have visualization, and you have machine learning. So it's pretty comprehensive stuff. And in the prerequisite, you had to install this Anaconda, which is essentially a distribution. So some guys that they rationalized and made sure that all these packages interact very nicely. Okay, so you can download the code we'll use at this GitHub address. It's github.com/Gigo, G-H-E-G-O, /ODSC_intro_2_data_science. I could have put ODSC, but I didn't think about it. Simple. G-H-E-G-O. You can just do git clone of that link. Sorry, I'll put it up again. Is there anybody who has never used Git and has no idea what I'm talking about? Yes? Okay, so ask the person next to you if she can help you using Git. And if she can't, move next to somebody that knows how to use Git. Okay. Oh, you're on the phone, so. Okay, perfect. It's a simple way of managing source code. and sharing it with other people. Okay, so here. All right. So this is what we're going to do. We'll take a data set that is by now pretty famous. How many of you have seen the Titanic cargo data set? Raise your hands. Woo, great. Nobody has seen it. Okay, so it's a very famous data set, actually. It's used extensively to basically learn the basics of data science. And what we'll do is we'll learn how we can explore it. Okay? We'll build a simple predictive model. So that's step number 3 of our process. And then we'll iterate and improve the score. And maybe, if time allows, we'll do a short competition inside the room to see who scores the best model. Okay, but let's get started. First thing is do this. Git clone of this address if you haven't done it. Then from the terminal, you cd into that folder. And then also in the terminal, you type IPython notebook. And that should open a window like that. Localhost, this. So you should see something like this. And if you click on the Titanic Survival Workshop IPython notebook, it will open this, which is what I was showing. So how does... Who didn't get here?
I'm not here.
Okay, let's troubleshoot this.
The thing is long. I need
Huh?
I need time to copy it.
Say again?
I need to copy the whole thing. Unless there's some way to copy to.
You do need to copy the whole thing.
Address?
Huh?
How do I get that address? Other than just do I just type it? Or
Okay, let me help you. And if you're not there, ask the person next to you to help you, and not be walking around until we all get there.
so I just don't have the address. That's it.
Anyone else? Yeah.
Oh, you don't have a geek.
Right. Everyone else who doesn't see that?
Having it close. Okay.
Nothing.
Yeah, you have to install the key.
Okay, for those who don't have Git, the simple solution is you go, you type here GitHub, download, and you download GitHub Desktop, which in my case is going to be for Mac, but if you have Windows, it's going to be for Windows. You download it and install it, and it will basically, once you launch it, look like this. Let me show you. It will work. Okay, why didn't it allow me to see it? Okay, you can't see it, but let's mirror it. 1 second. Okay. So if you download GitHub, it will look like this, and then in the link I gave you, github.com, here you will see this repo, and here you can do cloning desktop, and you will clone the folder. That's the simplest you can do.
Is it different from just downloading the zip?
No, if you download the zip, it's also fine. You can just download the zip and unzip it, and that's fine as well. And just CD into the folder. It's perfectly fine. Actually simpler than downloading it. Yes. Just download the zip as suggested. So if you go to oh yeah. Are we all here? Okay. So, yes, in the back, I'm coming.
This is reaching out.
Yeah.
And execute code in an interactive way. So if I double click on this, this is a markdown cell, so it's actually formatted text. And I can change it. For example, I can type, this is a big title. And then if I hit Shift Enter, or if I hit play here, same thing, it will execute the content of the cell, and since it's markdown, it transforms this in a markdown title. Okay? So I'll delete this. And then there are very nice extensions that you can use as presentation, for example. So to execute a cell, you hit Shift Enter. So I think we are all at this point where we all see the notebook, right? So you can hit Shift Enter and see what happens. The first thing we do is to import some libraries. So I go to the cell and hit Shift Enter. In my case, it will say 27 because I had run it once, but in your case, it should say in one. And actually, let's all be at the same pace. So let's restart mine. And get back here. So if I run it now, it will say 1. Perfect. Okay, so what am I doing here? I'm importing some of the packages that I will use, so pandas to use to import the data and manage the data. NumPy is useful for some functions, although I don't think I will use it today. And matplotlib is for plotting. And I also give a special command here with a % that tells that I want to see the graphs in line, so after the code in the notebook. Okay, so the first thing we're going to do is to explore the data set, which amounts to a bunch of different things. We need to load the file in memory, and then we want to look at what are the components, what are the features of the file. Identify the target and check for missing values. These are like simple things that you always have to do. Okay, so let's start from the first one. I load the CSV file into memory using pandas. And that's as simple as read CSV. And if you notice, this file is already present in the folder. So when you unzip it, it's there. So I call it DF. That's the short for data frame. But I could have called it John or Mark or whatever, it's just an arbitrary name. Okay? So what's the content of the data frame? The nice thing is I can use this head function or method and see what the content is. So head prints, I gave 3 lines, so it prints the first 3 lines on my table. And let's see what it looks like. So I have a bunch of columns. First one looks pretty much like an increasing integer, 1, 2, 3, and so on. It's called passenger ID, that's probably not so useful. Survive, I guess that's what I'm going to predict. And then I have a bunch of other things. And let's see what could they be. What could P class be? Huh? The passenger class, so it could be first class, second class, third class. Name, obviously, is the name of the person. Sex, male, female. Age, no need to explain. What could SUPERVISED stand for? Sibling spouse, yes. Whether or not passenger ID number 1, name Brown, Mr. Owen Harris, had sibling or spouses. Yes, he has 1. And part CH. People traveling either with sibling or spouse or with child or parents. Yes, that's parents of children. Then I have the ticket, the fare that they paid. What?
It's a terrible abbreviation.
Yeah, I'm not, my English is not good enough to understand the joke, but I guess it's a better abbreviation. Then you have cabins, and finally you have embarked, which probably stands for the port of embarkment. Okay? So let's see what kind of data these things are. There is a very nice method called info that I can call that shows me the content of a data frame. So for example, passenger ID, it's an integer. Survive, also an integer. P class, an integer. Name, sex are objects. When it says objects, it means it's a string. So it's text, okay? And then we have a float. Does everybody know what a float is?
But why age is in float?
Why age is in float? Good question.
Counts the months and the day.
Huh?
It counts the day.
No. That's a good guess, but it's actually, this is a technical reason. The age, the numbers are actually integers in the data set. But what do you notice here?
Not a number.
There are some age that are not present, and those are not a number, and not a number is a float. And so it has converted all the ages to float to make sense of the column. The column has to be the same data type throughout the column. Okay. So, and then we have cabins, which is an object, and embarked, which is an object. Okay. Yes?
So, is Python telling us based on the data, this is the data type? We are not telling this, right? So it's
Pandas is automatically interpreting it, but you can, if you want, specify, read this as a specific data type.
You can override it.
You can it tries to guess, but when you do the read here,
Okay.
so one quick trick I'll teach you. If you hit shift tab, it shows the documentation for the function, okay? So amongst all the options you can pass to PD read CSV, one is the data type, it's D type. I'm not sure what it is, but it's one of the options. Okay, so you can override, basically. Okay? Yes?
If you have a non-node, that does not push in same thing as non-number. If you could have, basically all I'm saying is you don't have any percentage, but when you do, you're using non-number for that.
Can you repeat the question?
In your age, for example, you have 700 being entries.
Yeah, that's missing values. You don't have the values.
Right, and then those missing values are, you're assigning them NaN instead of leaving them
Yes.
blank.
Yes.
Non means the different.
Once again, and I see there are only 3 ports of embarkment that are coded as S, C, or Q, and there are most of the people left from the port called S. Okay, so the target, I think we've already mentioned, yeah, it's survival. So survival, 549 people died, 342 survived. I actually didn't know that. I thought everybody died in the Titanic. And then I found out it was actually not the case. Seriously, when you hear about this tragedy, you think everybody died. Okay, so first thing I check is, are there any missing values? I go back to my info, which was really useful, and remember we've noticed that, yes, there are some missing values. Age is missing, and a lot of cabin information, and then 2 people only don't have the port of embarkment. Okay? Okay, so what do I do next? Wait. Okay, I do some mental notes of what I've discovered so far. I've discovered that there are 891 entries in my data set. Okay? 1 target column, and it's called survived. The remaining columns, I call them features, as we've learned. So the table, remember, there was features and label, or target. Okay? Of these, some are numerical, and some are text. 1 is completely useless. The passenger ID is just 1, 2, 3 is the count. 3 are categorical. P class is 1, 2, 3. Sex, male, female. Embarked, it's C, P, or S. 4 are numerical and above 0. That's age, the number of siblings and spouses, the number of parents and children, and the fare. And then there are 3 that I'm not sure what to do with. They kind of look complicated, or at least not obvious, that are like the name. Would it be relevant for predicting maybe there was an important family and got saved? Who knows? The ticket, maybe there was a lucky ticket. The cabin, I don't have most of the values. So basically, these first approximation, I ignore them. These I ignore. And these I will have to deal with. Age is only available for a certain amount of passengers, not all of them. And the cabin is only available for 200 and so passengers. Finally, there are 2 embarked missing. So I do some mental notes. That's like very preliminary exploratory phase. Okay? What do I do next? Well, for example, I do some plots. And since the age is the variable that is giving me trouble because it's missing, I decided to start with that. But I also want to check things like the influence of sex and the P class on the survival. Why is that? Because when its ship is sinking, who goes first? Women and children. And so maybe they followed that rule, and I'll be able to find that out and build a model that saves women and children first. So let's see. So plot the distribution of age. Pandas offers some plotting functions out of the box, and then I complement those with the matplotlib functions that allow me to set the title and the labels. So let's see what I'm doing here. I plot the age. What kind of plot am I doing? Well, I want the distribution, so I do a histogram. Raise your hand if you have no idea what a histogram is. Good, okay. So I do a histogram, and then I just do a bookkeeping here. I do the title, and I do the x-axis label, the y-axis label, and I also calculate the median age and plot a line for the median age. So if I execute this cell, well, what shows is a very nice plot of the ages and red line here, the median age I printed here is 28 years old. Also, the distribution is kind of weird, where, as expected, there are few children, and then at 18, it goes up. Okay, so as we said, we have missing values for age. So what do? Well, I do the dumbest thing first, because I want to get to the end with the simplest possible model and close the loop, and then go back and say, how can I improve it? So what's the simplest idea? Well, whoever I don't have an age for, I assign it the median age. That's as good a guess as any other. I could have done more complicated thing, but since I'm in the very early phase of model building, I just want to get to the end. So one hypothesis, as long as it makes sense, is a good one. So I fill the NAs with the median age, and I fill those in place, which means replace them in the column itself. Okay? And as you can see, if I do the F info again here, age now I have 891 not null values. Okay? Any questions so far? Yes.
Could you just take the 714 as your n instead of imputing?
Yes, you could do that. You could discard the rows of data for which you have missing data, and that's also a valid method. You know, in the preliminary phase where you just want to get to the end, that could be a valid thing. If you have 10% of data missing, that's, you know, preserves you of even having the hassle of deciding how to impute the data. Yes. Any other questions? What could be fancier ways to impute the data if I wanted to get a bit fancier instead of just guessing the median age? Yes?
Use machine learning to predict the age.
Okay, I could build a model that predicts the age based on the others. What's an intermediate thing that I could be doing? That's a possible way of proceeding, but it would be like using a tank to kill a mosquito, but yes. Yes?
You have the average for the children and the average for the adults and apply.
Yeah, I could do some sort of segmentation, so let's get the average for the children and give that to... the problem is, how do I know that they are children, right? You don't know that. But what you could do, for example, is instead look at the average age or the median age for males and females and assign those to the respective populations. That's a good possibility. What else?
And this is kind of interpolation along one of the data sets. Like on the age indexes, can you do an interpolation, something like that?
How so?
Interpolate it, like to smooth it out, just a curve going on.
You mean in this graph?
Along any of the heights, age, for example.
Yes. But how would you do the interpolation? Because there is no, I mean, the passengers are not related one to the other, right? So if a passenger is missing the age, how would you interpolate him? That's similar to what he's suggesting. You would need to build a model that predicts the age based on the other things. Like if you're in first class, you're probably likely to be older and wealthier, unless you're a child. Yes?
Maybe assign some integer value like 999 for the missing.
Well, that would not lead me any further than assigning not a number value, right? I would still not be able to use it as a feature. So I would just be calling it a different name. Yes?
I'd probably just weight it. So like, you know, 20% fall into age 20, then 20% of the, whatever it was, 800 minus 714.
Yeah.
I assume 20% of that is going to be 20.
So you would take this distribution and basically randomly sample in equal quantities. So if this is, I don't know, 10%, you would assign to 10% of the people age between 0 and 10, and so on and so forth. Yeah, that would be a fancier way of doing it, absolutely. And so on, and you can get, yes? You
can use the median now, since the Markov distribution. Instead of the average, use the median.
I use the median here.
Oh, you use the median?
Yeah.
Oh, I thought you used the average.
No, I'm using the median, exactly. You could use the average, but the median seems more appropriate because it's not symmetric.
Okay.
Yeah. As long as you can justify why you're doing that step, that's fine. There is no like definite answer. You could be throwing away the data because you need to go fast. You could be using a central estimator like the median. You could sample from the distribution. You could do a machine learning model to predict the age. Get as fancy as you want. Oh, here, okay. So let's see what's the influence of the age on survival. What I do here is I take the subpopulation of survived and of dead. I select the age column and I plot the histogram of the age into different histograms. What does it look like? Well, it looks like this, where, well, basically I've added a lot of median age here, so that's why this bar is higher. But the difference I notice is that the only place where the survived is higher than the dead is the very, very young children. So maybe there is some influence of age that if you're younger, you end up surviving more. Let's see. I can check the influence of sex. I defined the auxiliary variable survival by gender by doing a pivot table. So what does this look like? This looks like the counts of how many females died and how many males died and how many females survived and how many males survived. And what you notice is that you can see it in the numbers, but it's even clearer when you plot it. If you plot the survival by gender, with the bar chart, these are the females. Well, a very large fraction of them survived, and these are the males, and actually a much smaller fraction survived. So the simple guess of children and ladies first seems to be, at least in a very first analysis, seems to be confirmed. Okay? Remember, I'm not building models yet. I'm just scouring for ideas and formulating hypotheses on what could be the contributing factors. Okay. This is not sex, but it's P class. Okay. So I do the same thing for B class. I say survival by P class, and I do exactly the same thing. And what do I see? Well, so this is first class, second class, and third class. So in first class, more than half the people in first class survived, whereas in third class, almost everybody died. Let's say a fifth of the people survived. So maybe not only ladies and children, but also each first. I don't know what the guess is there, but there is some information there. Okay, so what have I found from this very simple exploration? I found that age and P class seem to have some influence on survival rate, and also gender has influence. So let's build a model that uses that and let's try to see a prediction. Well, first of all, I defined, if you remember, the sex variable. If I do here, let's just take a cell and do head. It's a string. It says male, female, right? So that's not what I want, because what I want, oops, what I want is a binary variable like 0 or 1. So I define a new feature called male, and this feature will be 1 if sex is equal male and 0 otherwise. So it's very simple actually to do it. I create a new column, VF male, it doesn't exist, so it will be created. And I set this column equal to what? Equal to sex, where I apply a map that transforms the value male with 1 and the value female with 0. So if I do this, and I do then VF male head, I see that it's 0, 1. And if I want to check that I actually did it correct, I here do sex and male and, oops, missing a parenthesis. Yeah, so, okay. So basically we need to do better than this 62%. That's our goal. Okay? Alright, so I define two auxiliary variables that are x and y, and those are like the features and the target. And it's as simple as selecting the corresponding columns. And then I will use a decision tree just because it's simple. So I could use another model, but to make it simple I use a decision tree. And here it's as simple as one line. I import the decision tree classifier from the scikit-learn package, and then I initialize it in a variable called model, which is decision tree classifier. I set the random state equal to 0 just because I want all of you to get the same results as I have. So we'll all get the same result. This is because randomness on a computer is not really random. There is an underlying generator that, if you set the state, will give the same random number to all of us. Okay? So that's just for demonstration purposes. So I initialize it, and I can see what it is by saying model, and it always prints the last line. So if the last line is just a variable, it will show me the variable. So it's an instance of decision tree classifier of certain parameters. These are the default parameters of the model. Okay, then remember the question was like, how do I evaluate if my model is doing well? Well, I need to split the data into training part and test part. Okay, so I arbitrarily decide to use 80% of the data for training and 20% of the data for test. And scikit-learn has a very nice function called train-test split that does exactly what I expect. So I give the features and the target. I define the test size of being 20%. I also set the random state equal to 0, so you all get the same results that I do. And then the output is going to be x train, x test, y train, y test. So I execute that, and it has split my data. So next, I train the model. Take the model that I have defined before, and I feed it with the training features and the training labels. Okay, so it's still a decision tree classifier, same thing, but now it has been trained. And now I calculate the score. And the score is also a method of the model. So the score I need to calculate it on the data that I had saved, so the test data set, with the test labels. Yay! 82%. Okay, so I'm doing better than the random guessing. So my model is good, but is not perfect. I am getting only 82% of correctness total. So if I want to dig a little deeper, I do this confusion matrix that we talked about, where I print how many cases I get correct of each case. So I see that I have 97 and 49 true negatives and true positives, but I still have some false positives and some false negatives. And notice how it works. Is the confusion matrix of the test and the predicted. Where predicted, I predicted using the model. Okay, so we got at the end of the guided part. Now there is a part where you get to play with the code and improve it. The way I was suggesting we do it, I've given you a couple of directions in which you could explore, and there's a script in your folder. You can either edit the notebook if you want, but otherwise there is a script here. It's called Titanic Starter Script. So if you open this, it only has the relevant steps, so it reads the data, inputs the median age, and then defines the features and target, initializes the trees, and splits the train test, and then fits the model and prints the score. So if you open a shell in here, let's make this big, you can do Python Titanic Starter Script.py, and it will just run the whole thing through and print the score and the confusion matrix. So you can either modify the script or modify the IPython notebook. Both are valid. The way we proceed is you can pair up in teams of 2 with the person next to you and brainstorm of things you could change. So here are some suggestions of things you could do. Where is it? This is the only bad thing of this presentation, is it doesn't allow you to go to the end. At least I haven't found a way to do that. Okay, so here are some ideas. You could add new features. For example, you could add the embark port. The way you would do it is by creating so-called dummy columns, which are columns that have a 0 or 1 corresponding to the embarkment port. So one would be dummy S, and it would be 1 if in the embark port there was an S in the corresponding row, and 0 otherwise. Then there would be the dummy C, and same thing. That's an idea. Another idea, you could just be tweaking the parameters of the decision trees. There are some parameters which are like the number of, the minimum number of leaves that you accept. So can you accept a leaf that has only 1 data point, or do you accept a leaf that are only bigger than a certain size? Or the maximum number of trees that you can have in depth. You can play around with those models. For those of you who want to dare, here at this link there is a comparison of a lot of classifiers with the respective code. And so you can, instead of using a decision tree, use another model and say a logistic regression or a support vector machine, and see if you can improve the score. The goal is to do more than 82% correct. That's what I got with very simple model. Okay? If you have any questions, I'll be floating around the tables, so to help you. Pair up, and or if you want to play solo, play solo.
I just did that, so I just
Oh, one final rule to make this more fun I'll have a leaderboard here, so whenever you get more than the current score, you raise your hand and you say your name, and we'll have a little contest.
Okay, so some notes. That sounds good. How about then cleaning up
What else do you use for that kind of data environment?
Important. So, if see whatever sense. My idea is change. Do something more
You might want to assign assign the analysis.
Yeah, sure. How can you do that?
Just go back. You just replace it. So just execute this.
Maybe because the variance.